Alright, so we talked about alkanes and how everything's single bonded, everything's flopping around because they're very flexible bonds. And they have what we call sigma bonds that are holding together. The sigma bonds are extremely strong. Now we're going to get into the two what we call unsaturated compounds. What I mean by that is that alkanes are considered saturated because they have a maximum number of hydrogens that can bond with carbons. Alkenes and alkynes are unsaturated because they have less than the maximum number. In other words, the number of hydrogens they're going to have is going to be less than the number of hydrogens in an alkane. And let me show you why. If you take a look at a 3-carbon alkane, this is called propane. And the formula for that is C3H8. You see 8 hydrogens around there. If I take the hydrogens off this, but leave 1 electron behind for the hydrogen, or for the carbon, rather, and link that up over here, we create a double bond. So it looks like this. Now, we've lost a pair of hydrogens because we created this second bond of the double bond. So the formula for this is C3H6. Now, the general formula for an alkane is CnH2n plus 2. In other words, you double the number of carbons and then add 2 to get the number of hydrogens involved. Here, as you can plainly see, is CnH2n. And that is true for all the alkenes. That's the general formula for alkenes. And that's because you lost 2 hydrogens to form this extra bond. Now let's talk about that extra bond. In this case right here, with all these hydrogens, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pi bonds. Or I'm sorry, 10 sigma bonds. 10 sigma bonds. But when you create a double bond, you have the sigma bond, which is because it's most likely, although not 100% of the time, just like all these over here, is a result of s electrons overlapping. In this case, you've got, remember you have p electrons that are also involved in the outermost level, and they're overlapping and creates what we call pi bonds. Now, these are not reactive for all practical purposes, except lighting them on fire. This is much more reactive than this because of the presence of that pi bond. That pi bond is pretty weak. So when a collision occurs with other molecules with propene, the collision has to occur at that double bond order for reaction to take place. We call that an addition reaction, where the molecule that collides with it breaks apart. The pi bond that breaks apart forms 2 electrons, 1 on each carbon, and then forms bonds, single bonds, with the substances they react. That's called an addition reaction. You're adding the atoms across that double bond. You create an alkane with something added to it, which is something we'll talk about towards the end of this chapter. Okay? Now, so in this case then, you have 1, 2, 3, 4, 5, 6, 7, and that is the sigma bond right there. You get 8 sigma bonds, and then you have 1 pi bond. But we just consider that a double bond because it's 2 bonds wrapped up in 1. It's 2 bonds in 1. I used to be really good at this in college. That's why they used to call me Bond. Okay, so let's take a look at the Alkene versions. We have a triple bond. And the formula for this is C3H4. Why? Well, again, we're going to take these remaining 2 hydrogens, get rid of the hydrogens, leave 1 electron behind, and they overlap to form a second pi bond. so you've got a pi bond on the outside, pi bond over here, and a sigma bond here. Now, it isn't layered like that. In fact, it's more something like this. When you see this, you have the main bond, you got one here, you got a pair over here, and then there's like a cloud around it as well, where you have bonding and what we call anti-bonding. Anti-bonding is not where you find electron, the bonding is. It's a little complicated, but trust me when I say, we have two pi bonds here and one sigma bond. So we count the sigma bonds, 1, 2, 3, 4, 5, 6 sigma bonds, and we have 2 pi bonds. Now, another thing I want to show you the difference between an alkene, alkyne, and alkane. Now, this is an example of an alkane. I'm going to simplify this just a fraction here. I'm going to make this a butane. And so as you can see, these bonds, this is just like how they would actually handle their situation here, because the sigma bonds are so flexible. But if I were to replace there it is. If I was to replace one of the sigma bonds with the double bond, so, the butane I had there to begin with now becomes a butene. But this, check this out, this is not flexible at all. Not flexible at all. So, this lends itself to orientations in space that are different, which causes different names. Now, we're going to get into that in the next section. But this is not flexible. It stays intact as that. Okay? So, and then the triple bond is even stiffer. It looks like this. There's zero flexibility. You can slightly bend this if you want. There's a certain amount of bending that can take place, but this is absolutely stiff. It's not going to place. So the geometries that are created are completely different. Now remember, alkanes are all 109.5 degrees tetrahedral. They all form these, four-sided figures around them. At the location here, you can see this is 120 degrees and triangular here. That's at the triple bond. This over here, of course, flexible, 109.5 degrees tetrahedral. And this is linear right here and tetrahedral right here. So I don't know if you remember that from your Vesper days when we were doing that, but that's kind of important. Okay, so next thing I want to bring up has to do with how we can identify names of isomers. They have the same number of carbons and hydrogens, but different number of structures. So if I go back to, let's take the butene, okay? And remember, every carbon needs 8 hydrogens on it. And with the Lewis dot structure, we're using the north, south, east, west directions, even though that's not true what they really look like. But if I take this pi electron here, or pi bond here, and move it over here, which does happen, we get this. Now, they're both C4H8. Not 18, that would be ridiculous. C4H8. but they're not the same thing. As you can tell, the single bond is here. The double bond is here, the double bond is here. This is actually between carbons 1 and 2. Now remember, IUPAC states that you always use a lower number when possible. So this is going to be 1 UT. Because between carbons number 1 and 2, so we'll give it the lower number. This is between carbons 2 and 3, so this is 2 UT. Okay? Now, another isomer for this, if I take this right here off this and put it right there, I would get this structure. This is also C4H8. The longest continuous chain here is 3. Now, when you have a longest continuous chain, when you start dealing with unsaturated compounds like alkenes and alkynes, the longest continuous chain must include the double or triple bond. So in this case, this is right here the longest continuous chain. So this is a methyl group attached to the second carbon. And so this is going to be on the second carbon. So this is 2-methyl. And then this is a propene, and this double bond is on the first carbon. This is 1-propene. Now, I put numbers on there just to emphasize where they're located. In actuality, this particular compound needs no numbers, because you can't have a 2-propene in this setup, and the methyl group can only be on the second carbon. So technically, the correct name for this is methylpropene. I'm not going to get too concerned about that here, but I will tell you, your organic professors who take organic in college will have a hissing fit if you do that. If there's no ambiguity, then IUPAC states use numbers. If there is no ambiguity, then this is the correct answer. And there is no ambiguity wherever it is here. But you're just learning the system. I'm going to allow you to use the numbers. Then once you get in the habit of looking